In this sequel of this video, lecture, we have covered preliminary part of vector calculus, and now we will discuss about vector calculus. Now in that, we have to find out derivative of vector quantities. U bar, v bar and omega, these are the vector valued functions, and we have to find out its derivative with respect to t, because all these are the functions of t, and phi and psi, these are the scalar valued functions. Then some properties are there. These properties are, if we are finding derivative of k into u bar with respect to t, we are taking k outside, k is constant, du bar by dt. This is simple property, just we are knowing in our real algebra. Du bar by dt, phi into u bar. Again we are finding this derivative just like our derivative. We are taking phi, first of all derivative of first term, keeping second term as it is, plus keeping first term constant, finding derivative of second term, but this is in terms of vector form. Again, derivative of addition of two vector quantity, this is linearity. This is the derivative of u bar plus or minus derivative of v bar. Here minus sign is there, then we can take minus. Derivative of dot product of two functions. Again we are finding, this is just like a product rule. We know how to find out product rule. We are taking derivative of first term, keeping second term as it is, plus derivative of second term, keeping first term as it is, and then. But we have to keep this product sign as it is at this position. Means here we are finding derivative of first term du bar by dt, and we are keeping dot v bar as it is. Plus now we are keeping first term as it is, dot derivative of second. Then in dot product, you can write here dot anywhere because dot product is commutative. A bar dot b bar is equal to b bar dot b bar. But this is not a case for cross product. If we are to find derivative of cross product of these two functions, then we are finding derivative of first function with cross product with b bar as it is, plus we are keeping first term as it is, cross product into derivative of second. Now in box product means we have to find out derivative of three terms, and we are knowing that in our real calculus we are finding derivative of first term keeping second and third as constant, plus derivative of middle term keeping first and last as constant, plus derivative of last term keeping first and second as constant. Here we have to take omega bar. U bar is here, we have to rewrite here again. But here when we are taking derivative for this vector quantity term, we have to keep dot and cross at its own positions. Now how will we find this derivative? We have to find derivative of first term keeping dot b bar cross omega bar as it is, plus we have to find out derivative of middle term, this u bar dot and this cross term we are keeping as is. Then we have to find out derivative of last term keeping u bar dot b bar cross product with this derivative. In similar way, we can take derivative for vector triple product, and this first one was the derivative for box product. Again here also we have to do the same thing, and we are taking cross and cross this stuff as it is for this derivative. Here, sorry to write here. Here we have to take cross product instead of dot. We have to write here product. This is simple property. As per our derivative, we are knowing how to find out derivative. Same thing we are doing. Now important thing is this operator del. This is an operator del. This operator del is defined in this way: I into partial derivative with respect to x plus j into partial derivative with respect to y plus k into partial derivative with respect to z. This operator del containing ijk terms, therefore this is a vector function. And this operator del is operating on scalar function part, then total becomes a grad. This is the gradient of phi. The gradient of phi is denoted by this notation also, del into phi. This is called grad phi. Grad phi is I into dou of phi beta by x plus j into dou of phi beta by y plus k into dou of phi beta by z. And this is a vector quantity. Keep in mind, gradient of phi is a vector quantity. Again, some properties of gradient. This operator, this k into phi. This k is constant. Then we can take k outside, and we are getting gradient of phi. This is equal to 1. Plus or minus terms are there, means gradient of phi plus psi. This is again linear property holds. Gradient of phi plus or minus psi is equal to gradient of phi plus or minus grad psi. When we have to take product of these two functions, phi into psi, they both are scalar term, therefore this is phi into psi, and if we are operating this operator del on this, then we have to take just like our derivative rule for product function, and take here phi into this operator del on psi plus psi into this operator del on phi. Again here quotient rule, just like derivative for quotient rule, we can write here psi into grad phi minus phi into grad psi divided by psi square. Moreover, the psi should not be gradient of f of u, and this u is function of xyz and f is function of u. In this case, we can find gradient as first derivative of f dash of u into grad u. This 8 number we are using here equal to some types here. d phi is equal to grad phi dot product with dr bar. d phi, this is for total derivative d phi, is equal to grad phi dot product with dr bar, where r bar is xi plus yj plus z. Usually we are taking r bar, the position vector for this identity point x, y, z. R bar is xi plus yj plus zk, and dr bar, how we are finding dr bar? This is the dxi plus dyj plus dzk. This is dr bar, and we are taking dot product of grad phi dot product with dr bar is nothing but d phi. Dr bar is a tangential direction to that curve at that point. And here, if every time in usual case we are taking this phi as a leveling surface or equipotential surface, then this d phi becomes 0. Means we are here real existence. This is a leveling surface or equipotential surface. Then this derivative becomes 0. Then we are getting grad phi dot dr bar is equal to 0. That means here dot product of these two vectors is 0, means these two vectors must be perpendicular. dr bar is a tangential direction, and this is a perpendicular to this tangential direction. That means gradient of phi is a normal direction. So this is a normal to this tangential direction. Therefore, I am taking here gradient of phi is along normal direction to this surface phi, and derivative. This derivative is also sometimes called tangential direction. Now direction, this 10th number is very important. Surely problem is there on this. Directional derivative of phi along the direction of vector a bar is gradient of phi dot product with a cap, unit vector to this a cap. This 11th one is gradient of r raised to n is equal to n into r raised to n minus 2 into r bar. Directive formula, gradient of r raised to n is equal to n into r raised to n minus 2 into r bar. This is about gradient of vector. Now after again here remember this, grad is a vector quantity and gradient is along normal direction. Now next part is here. After this gradient of scalar function, we will discuss this operator del and vector function. Now operator del is vector, u bar is vector, and either we have to take in between dot product or cross product. If we are taking dot product, then this becomes a divergence, and here divergence of u bar is del dot u bar. We are taking dot product, and here dot product, this is scalar quantity, dot product of two vectors. And if divergence is 0, this is important. If divergence is 0, then u bar is a solenoidal. Solenoidal means this is incompression. No compression is there in this flow. If viscous fluid is flowing through the pipe and no compression is there, then we say that divergence is 0. Curl of u bar. Curl of u bar is a cross product in between this operator del and u bar. If suppose sometimes this curl is 0, this is vector quantity because cross product is 0, then u bar is irrotational. Keep in mind, sometimes they are asking about this curl is 0 or divergence is 0. This is simple identity. Divergence of r bar is always 3 and curl of r bar is always 0. These are the simple identities are there. But here this one is important. Del square of f of r. Del square of f of r is 0. Then this function satisfying Laplace equation, because this del square is called an Laplacian operator. The del square of f of r is 0, then f of r satisfying the Laplace equation. Sixth one is very important. Sometimes they are directly stating, directly giving the results, and they are asking what will be the result of curl of grad phi, divergence of curl of u bar. All these are these things. And if we are knowing that by satisfying Laplace equation, then we can write divergence of grad phi is equal to 0. So we are getting messages like here, del dot. This is divergence of grad, this function, and divergence of grad function is 0. Then this phi satisfying Laplace equation. Divergence of integration of f of r is equal to f of r into grad r. We are not using this. Now next part is here some identities of vector quantity. First two identities are just linearity, based on linearity. Divergence of u bar plus v bar is the divergence of u bar plus divergence of v bar. Curl of u bar plus v bar is equal to curl of u bar plus curl of v bar. The third and fourth one are somewhat important. Divergence of phi into u bar is equal to phi into divergence of u bar plus u bar dot grad phi, and curl of phi into u bar is equal to phi into curl of u bar minus u bar cross grad phi. In some books, this identity they can write here grad phi cross product with u bar, and here sign plus. So we will make that cross product of a bar cross b bar is equal to minus of b bar cross. That way, if you are switching this, then you will be able to take this. If that's it, then we are not. Now then integration part for this vector integration. Line integral is, that means this line integral is called work done, and work done we are knowing that force into displacement. But if we have to find out work done along the curve, then we can take integration. Under this integration of c, the part dot dr bar is called our line integral. Keep in mind, dr bar is nothing but tangential direction to vector r bar. R bar is xi plus yj plus zk, usually we are taking this, and dr bar is a dxi plus dyj plus dk. Now after this line integral, Green's theorem. But remember that when we are using Green's theorem, this r, this region r should be a closed region, and C is the boundary of this closed region. C is the boundary of this closed region. Then we can apply Green's theorem. To apply Green's theorem, this region R should be closed, and this C is the boundary of this closed region. Statement is u into dx plus b into dy is equal to double integration double v by double x minus double v by double y into dx dy. How to remember this? This v into dy. V is the coefficient of dy term. Therefore, we have to partial differentiate with respect to x minus u is the coefficient of dx term. This is dx, that we have to differentiate partially with respect to y and dx. This theorem gives the relation between line integral and this surface. Now Stokes theorem. Now main thing, important thing for the Stokes theorem is Stokes theorem gives relation between line integral and surface integral, means single integration and double integration. In this surface integral, S should be open-ended curve, open-ended surface, and C is the boundary of that open part. C is the boundary of this open part. Means here, if one end is open and C is the boundary of that open end, then we can apply Stokes theorem. Means we are applying Stokes theorem when surface whose one end is open and C is the boundary of that open end. Otherwise, we are not applying this Stokes theorem. Here, statement of Stokes theorem is integration over C f bar dot dr bar is equal to double integration minus curl of f bar dot product with n cap into dx. This theorem gives relation between line integration and surface integration. Moreover, this surface should be open-ended and C is the boundary of that open end. Gauss theorem or Gauss divergence theorem. In this Gauss divergence theorem, our is yes, surface should be a closed. Yes, surface should be a closed surface, and we are finding volume of this closed surface. In this theorem gives a relation between double integration and triple integration. That means surface integral and volume integral. This theorem gives a relation between surface integral and volume integral. This S should be a closed, but in Stokes theorem, this S should be open-ended and C is the boundary of this open. Here, this S should be a closure, and for this closed region, we are taking volume of that. The statement of this Gauss divergence theorem is double integration over S, FR dot product is n cap into S, which is equal to triple integration, means volume integration, divergence of FR into D. Here we are using divergence, therefore this is called divergence or Gauss divergence theorem. Sometimes this n cap into ds, we can write ds bar. Here ds bar is equal to, here should be equal to, ds bar is equal to n cap into ds. Now this is the preliminary part of this. Again I will recall this preliminary part very fastly. Here magnitude, dot product, cross product, box product or scalar triple product, vector triple product. These are some basic identities of this vector algebra. Then some properties of derivative of this vector function, gradient function, divergence and curl, some identities of this divergence and curl, vector integration, line integral, Green's theorem, Stokes theorem, and Gauss. Now, after this, we'll discuss about examples, and this is the very example based on the preliminary part. We'll discuss about this first example. The vector that is not a perpendicular to the vector I plus j plus k and I plus 2j plus 3k is, options are given A, B, C, D, which is not a perpendicular. We are knowing that condition for perpendicular of these vectors. If vector their dot product is 0, then we are saying that these are the perpendicular. We have to find out which not a perpendicular to these both vectors. Suppose I will take this first vector and I will take just direct dot product with these options. I will take A option and first vector I plus j plus k and this I minus 2j plus k. I dot I is 1, minus 2 and j. Here this is minus 2, k dot k is 1. Means here we are getting this 1 minus 2 plus 1. 1 minus 2 plus 1 is 0. Means here surely A option is not there. Because this is a perpendicular, we need a not perpendicular. If we are going similarly for second option, we can take for any vector. First vector is minus 1, this is plus 2, j dot j, and this is minus 2. Means here minus 2 plus 2, this becomes 0. 0 vector is C option. Remember that 0 vector is always perpendicular to every vector. Therefore, no need to check here for this. Now for last option, 4 plus 3 and this is plus 5. So 4 plus 3 is 7, 7 plus 5 is 12. This is not 0. Therefore, this is not a perpendicular, therefore our D answer is correct. And we are knowing that this property of this dot product or perpendicular vector or orthogonal vector, and just dot product in between two vectors, they are vector. And D is our correct option. So again, please read carefully, not perpendicular. All these three vectors are perpendicular, but only fourth is not perpendicular. You can take for this vector, or also you can check for this vector. This was again asked in last exam. Now we take this second example. With velocity field of incompressible flow is given by This is our vector a1x plus b1y plus c1z into y plus a2x plus b2y plus c2z into j plus a3x plus b3y plus c3z into k, where a1 is equal to 2 and c3 equal to 4, and value of p is options are not given, space is provided, and we have to write our answer. Now when we are reading this, velocity field is incompressible. What is meaning of incompressible? We are knowing that incompressible means their divergence is zero. Their divergence is zero. Means divergence of v bar is zero. This is solenoid. Divergence of v bar is zero. Only we have to take divergence of this vector is equal to zero and find out divergence and compare with zero is equal to zero. But again, keep in mind, when they are asking problem in your GATE exam, this problem is very simple problem. Only observing also we can find its answer. But sometimes they are twisting that. Again, here nothing is given, only incompressible fluid is given. That means here this vector field whose divergence is zero. Here solution is, we are taking divergence is zero, and how we are finding divergence? Find derivative of this first component with respect to x plus derivative of second component with respect to y plus derivative of third component with respect to z. Okay, derivative easily we are getting, orally we can find its derivative with respect to x is first term a1, second term derivative with respect to y is b2, and third one is c3. And this is given, a1 is 2 and c3 is 4. a1 is 2 and c3 is 4. And this is equal to 0 because divergence is 0. And therefore we are getting b2 equal to 2. Okay, thank you friends. In coming lecture, we'll discuss again new problems from our last GATE exam. This recalls our idea about vector calculus and helps to score in our coming GATE exam. Okay, thank you. Go towards our next coming lecture.